So as we move into Chapter 9, I have a bit of a confession to make. We've been cheating. For the past few chapters, we have been cheating when it comes to our systems and basic Newtonian laws. We have been assuming, without me telling you, that every object we've been dealing with is point-like. Okay? That is to say that all of the mass is concentrated at a single point on the particle. Now y'all know that that isn't true. Okay? As I reach off screen here and I pull out this wonderful candy cane full of Snickers that I've been eating a little too much, and I'll put on a little bit of weight during the Christmas break, and thank you for noticing if you have. I'm a little sensitive about it. But we know that this thing is not a single point in space. This thing has a mass distribution all over it. There's mass up here at the top of the candy cane as it moves down. We see that we have the Snickers inside here, okay, and they're kind of concentrated down here. So one end of the mass is actually heavier than the other end. We also have different types of material inside of this candy cane. Up here we kind of have a plasticky bit. Down here we have a hollow plastic bit. And then of course we have the Snickers candies down inside there. And if you go even deeper with this, you have Snickers candies that have peanuts inside of them. Are those peanuts evenly distributed? No, they're not. Okay? For another example, think about your car. Okay? When you're sitting inside of your car, you are a piece of mass inside of that car, correct? You are going to influence what is going to happen to that car. If you have somebody who's a little heavier and they get into the back of the car, you can actually see the car rock backwards a little bit. So up until now, we've been cheating. All the boxes that we've been pushing inside of these physics classrooms, everything we've been doing, we've been treating as a point-like object in space. Now, the way we've been able to do that is this idea of the center of mass, which is locating a point where we can treat all of the mass to be located at that single point inside the object, and we can apply all external forces to that center of mass. Okay? So this is a kind of a weird concept. It's a little hard to grasp the first time. But remember, you guys understand that different pieces of material have different balancing points, correct? So if I go back to the candy cane argument, you can find where there's a balancing point where I can actually place my finger in such a way that the candy cane will balance itself, okay? Now it's kind of hard to do. You guys can do it with your pencil right now, and I suggest that you do it. But as I try to find the balancing point, when I find that balancing point, and I probably should have practiced this a little bit, when I find that balancing point, that is the center of mass for the object. That's the point where I can treat all of the mass to be located, and all external forces are being applied to that center of mass position. So it's kind of a way of condensing down these objects that have density, that have different materials, condensing them down in such a way that we're going to treat them as a single particle in space. As we move into later chapters, when we start dealing with rotations, we will not apply those forces at the center of mass. By not applying those forces at the center of mass, that is going to force us into rotational situations. You're all going to get very upset with me because that stuff is very, very complicated, but let's deal with this right now. We will come back to that. So when we're dealing with center of mass problems, the first thing we're going to say is that all mass is concentrated at a single point. So number one, all mass is concentrated at a single point. So we're going to say all the mass is concentrated at a single point. That's the balancing point from the candy cane just a minute ago. If I put my finger right there, I have an equal amount of mass on both sides. The system balances out. Okay? So that's the first idea for the center of mass. The second idea is that all external forces are applied at the center of mass, COM. All external forces are going to be applied at the center of mass, COM, center of mass. That is because, as I said a minute ago, if we don't apply those forces to the center of mass, that's going to create a rotation in our system. We're not dealing with rotations just yet, so we don't need to worry about that. Calculating the center of mass for a system of particles is rather straightforward. It's not that bad, okay? If I have a coordinate system, and let's say all of my masses are concentrated to an x-axis right now, the x center of mass, the position of the center of mass along the x-axis, is equal to 1 over the total mass multiplied by the sum from I equals 1 to n, because I could have many masses, many individual masses, but I need to consider each one, multiplied by mi xi, so that would be the individual mass, little m, so the individual mass in question, its position, and I'm going to sum up all of those guys, okay? All of those masses. So this is how I find the center of mass along the x-axis. Again, it looks weird, so let me actually come in here and do a quick example. So in this quick example, we have an x-coordinate system. So here we're going to be at 0 meters, here we're going to be at 1 meter, and we're going to have a 4 kilogram mass at 1 meter, and then a little bit away at 3 meters, we're going to put another 4 kilogram mass, okay? So I have one 4 kilogram mass at 1 meter, and another 4 kilogram mass at 3 meters. Now remember what the center of mass stands for. It stands for the balancing point. Now it's really easy to think about where the balancing point would be. If I were to consider this to be like a seesaw, okay, you got one friend over here with 4 kilograms, the other friend over here with 4 kilograms, the midpoint should be the center of mass. That would be the balancing point, correct? If you guys take your pencil right now, you can actually find that balancing point. It's a little off of the center of the pencil because if you think about it, your eraser has a different density than the very tip of your pencil where some of the wood has been shaved away, but it's very close to the center. So we know that the balancing point should be at 2 meters. But let's test this with our center of mass calculation to make sure that this makes sense. Okay? So the x center of mass is equal to 1 over big M. Big M is the total mass. So the total mass, 4 kilograms, so 1 over 8 kilogram. Now I need to multiply the individual mass, 4 kilogram, multiplied by its distance from the 0 point. So this would be 4 kilogram at 1 meter. Plus, now the other one is 4 kilograms at 3 meters. 4 kilograms at 3 meters. Now notice what's going to happen in here. I've got kilograms here in the denominator. I've got kilograms here and here in the numerator. So my answer is going to be given in meters, which makes sense because this is the position of the center of mass along the x-axis. So that should make sense. So now I'm going to have 1 over 8, and we're going to multiply that by 4 times 1 is 4, 4 times 3 is 12. Please check my math, make sure I'm okay, even though you're not here right now and I can't hear you, you should probably check my math. And so the x center of mass is equal to 4 plus 12 is 16, 16 over 8, which is equal to 2 meters. So we got the exact same balancing point that we were expecting. The exact same balancing point that we were expecting, which is really good, okay? So that should make us feel really good right now. We can also do the y position of the center of mass and the z position of the center of mass. So we can make this a 3-dimensional coordinate for the center of mass, for the balancing point. In order to do this, the y center of mass is going to be equal to 1 over capital M, the total mass. So it looks exactly the same, the sum I equals 1 to n of mi, except now I'm summing them over the y coordinates. And then for the z, all I do is swap in this yi for zi, so the z center of mass is equal to 1 over m, the sum from I equals 1 to m, mi, zi. So that is how I would get a 3-dimensional coordinate for the center of mass, okay? Remember, 1 over capital M, that M stands for the total mass of your system. Then we have mi, xi, so we're going to multiply the individual mass by its coordinate. If I'm dealing with the x-coordinate, I deal with the x-coordinate right here. And we get an answer that is given in meters. That makes sense because we're going to be dealing with position.